Good morning, students. So far we have discussed about the field equations, so which are very important in second quantization in quantum field theory. So we discussed about Lagrangian field equation in the last video lecture. Now in this class we are going to deal with Hamiltonian formulation. So we are going to arrive the field equation with Hamiltonian approach. And in the last lecture, we discussed about the Lagrangian field equation when we started with principles of least action, Hamiltonian variation principle, and we introduced Lagrangian density, which is nothing but the values of Lagrangian per unit volume. Then we used the least principal action. Then we derived the famous equation. So that equation exactly resembles with the equation of motion, see in Heisenberg picture. So this is what we discussed in the last video lecture. And we started with the second quantization and we discussed about the fields are quantized. So this is the base in second quantization. The fields are quantized. Fields means we can say about the electromagnetic field, electric field, magnetic field, and all those fields are quantized. In fact, they exist in the universe. And we know that creation and annihilation will take place continuously, and we can't say this is a fixed number. So this will never have a constant value. So one value will increase, then another value will decrease, and we can say that this will have infinite numbers, infinite degrees of freedom, infinite number of particles. So that's why we always go with second quantization in which the fields are quantized. So they live in Fock space. So this is what we discussed in the last video lecture. And here too, we are going to arrive the field equation using Hamiltonian approach. We know that in classical mechanics, while deriving Lagrangian form to Hamiltonian form, we define a momentum PA and conjugate to each coordinate QI. So for QI, there exists PI. So this is canonical conjugate variables which we studied already. So generalized coordinates. So here in quantum field theory, exactly it resembles with the psi. So Q is the generalized coordinate in classical mechanics, which will be replaced by psi, which is nothing but your amplitude, field function. So in quantum field theory we use this one, in classical mechanics we use this one. So this is your generalized coordinate and this is your amplitude, field function. Functor, yesterday we discussed about a functor. So it's a function of space coordinate and time coordinate. And also in quantum mechanics, in classical physics we use the generalized momentum PA, whereas in quantum field theory we are going to use as pi. So two canonical conjugate variables in classical physics, which is nothing but Q and P's. Here it is psi and pi. Is it okay? So you have to differentiate in classical physics. This is Q and P's, Qi and Pi's. Whereas in quantum field theory, this will be psi and pi. Okay, psi and pi, which we are going to discuss. So whereas in order to quantize the classical field theory, we must introduce the conjugate variables. So we are going to introduce the conjugate variables exactly as we have introduced the canonical conjugate variables in classical physics. Here we are dealing with the infinite number of degrees of freedom. So we know already corresponding to the values of psi, r, t, because the amplitude exists, it propagates everywhere in the space. So infinite numbers of degrees of freedom. Hence the momentum pi conjugate to the canonical coordinate psi I is defined by this equation. So according to Hamiltonian formulation, we are going to define the momentum, generalized momentum pi, which is equal to partial dl by d psi dot I. Okay, this is psi dot I. Okay. So in terms of functional derivatives, dividing into small cells of volume d tau I. So small cells of volume d tau I. So pi, the momentum pi can be written as exactly as it is, equation 10.24. So we know from Lagrangian equation for the system of particles, mechanical particles, we know this equation very well. Okay, partial d by dt dl by c d psi dot minus dl by d psi I, which is equal to 0, we know. Suppose if we consider this equation with small cells of volumes, then this equation becomes exactly like this, or otherwise multiply on both sides by d tau I. Okay, going to consider this system of particles with the small cells of volume, this equation will become exactly like this. Is it okay? Now dl by d psi dot del tau I is nothing but your pi. So this equation can be written as d by dt pi. This equation, this expression, let it be like this. Is it okay? Very simple one. Instead of this, you are going to write pi. So d partial dpi divided by dt minus the remaining term, which is equal to 0, which is nothing but equation 10.27. So this is nothing but your p dot. Okay, your p dot is partial dpi divided by dt. Is it okay? So pi minus the next equation, this will pi, your pi minus this one equal to 0. So pi equals this expression. So pi equals dl by partial dl by d psi I del tau I. Is it okay? Any doubt? So pi dot, already we know that pi is given by that one. We started with pi. Can you remember? And this is pi dot. You remember these two expressions, which are very important. And Hamiltonian formulation starts with exactly in this equation. So which you have studied already in classical mechanics earlier. So this is your ith component of generalized coordinate. Okay, pth state, this is your ith state of generalized momentum. The product of these two with a summation over I minus L will give you your total H. We know already this. Okay, so this is a relationship between Lagrangian and Hamiltonian expression is given by this expression 10.29. Any doubt? Okay, now we are going to write this equation in terms of field function psi I. So what is qi? Qi is nothing but psi r cum. So q dot is nothing but psi dot. So instead of qi dot, we can write this psi I dot. Okay, this is your field function. This is your generalized coordinate. This is in classical physics. Now we are going to write this expression in terms of quantum field theory. Okay, is it okay? Now we are going to define the conjugate field or momentum density. That's why I said the momentum density. Momentum density we are going to define as pi, which depends on r comma t, which is equal to dl by partial dl by d psi dot I. So this is momentum density. So there are two canonical conjugate variables in classical physics, which is nothing but q and p's. Whereas in quantum field theory, again two variables. Okay, which is nothing but one is psi, another one is pi. Okay, psi stands for amplitude, field function. Pi stands for momentum density. So don't forget. Okay, these two variables, they are those two variables. So your pi, which depends on r comma t, which is equal to partial dl by d psi dot I, which is equation 10.31. Any doubt? We have used pi equal to dl by d psi dot. You just bring this term down. So pi divided by del tau I. What is the meaning? Momentum per unit volume. So momentum density is nothing but the values of momentum per unit volume, which is given by this. So your pi will be pi divided by del tau I. Is it okay? Simple. Now using equation 10.24, so we have written 10.24 equation. This is 10.24. This is equation 10.31. This can be written as, instead of this you can write as pi. So pi, which is equal to pi r comma t, which depends on r comma t, del tau I. Is it okay? So I repeat, this expression can be written as pi. So pi equals pi del tau I. See, this is equation 10.32. Now you are going to substitute equation 10.32 in 10.30. This is 10.30, the Hamiltonian formulation. So you have H equals psi I pi minus L. So we can write psi dot Instead of pi, you can write pi del tau. See, pi del tau I. So pi del tau I minus your L. L can be replaced with Lagrangian density. Yesterday in the last lecture we discussed about Lagrangian density, which is given as this expression. So you will have minus sigma over I L bar I del tau I. Is it okay? That is the integration. Here we have replaced with summation. Okay. Any doubt on this expression? 10.33. Simple one. So now pull common terms out. We have pulled common terms out. Delta is nothing but your dq bar. So remaining term, let it be like this. And we are going to replace this term as this symbol h. Okay, this is ordinary h and this symbol as different h, and we are going to replace this term as h, where h is the Hamiltonian density. So in the last video lecture we discussed about the Lagrangian density, number of Lagrangian per unit volume. Just now we discussed about the momentum density, the values of momentum per unit volume. Similarly, Hamiltonian density is given by this expression. So Hamiltonian per unit volume, small variation of h can be written as. So this h I am going to have with a small variation. So del h, which is equal to del with the remaining expressions. Any doubt? 10.36. Equation 10.36. Very simple. Our aim is to find out the equation of motion. 1. The field equation using Hamiltonian formulation. That's all. So your del h is given by del multiplied by the remaining integrals. Okay. The variation of L produced by variation of psi and psi dot. We know that L depends on psi and psi dot. So we are going to consider L is the field function which depends on psi and psi dot. So we can use the product rule. We can use the rule. That is, we can use the differentiation rule, partial differentiation rule. So L equals L, which is a function of psi and psi dot. We are going to use the partial differentiation rule, which is given by this expression. Yesterday we discussed for two equations. Can you remember? So similarly, del L equals a partial del L by del psi plus partial del L by d psi dot del psi dot. Is it okay? Now integrating on both sides, you will get this one. Okay, you can integrate, and with respect to volume, you can write that equation exactly like this. Is it okay? I repeat. See here, L is a function of psi comma psi dot. Okay, so use partial differentiation rule, which says that first you will have to differentiate this one. Okay, then you will have del psi plus you will have to differentiate this, you will have del psi dot. Now integrate and with respect to volume. So you can write this expression 10.37. So now you have to substitute the expressions for del partial dl by d psi and partial dl by d psi dot. So we know that pi is given by del L by del psi dot, pi dot is given by del L by del psi. We know already. So substitute here. So instead of del L by del psi, we can substitute pi dot. So del psi let it be plus partial dl by d psi dot is given by pi. So pi del psi dot d cube r. Any doubt? Equation 10.38. Now you just take the second term alone. So what we are going to do is, we know that del pi psi dot is given as, use the product rule, which is nothing but keep this as constant, differentiate this, then keep this as constant, differentiate this. So you will have this, correct? You are going to keep pi as constant, differentiate this, plus psi dot as constant, differentiate pi. So you will have this. Now I am going to bring this term to that side. So I am going to keep this term here, okay, and I am going to bring this term to this side. So that will give me del pi psi dot minus psi dot del pi. So instead of pi del psi dot, I can write this term and this term. Is it okay? I repeat. So we are going to replace this term using this idea, which is nothing but del with the bracket pi psi dot. Use the product rule. Then keep this term here, bring that term here, that will give you this expression. So instead of this you can just substitute here. Okay, we know that H equals Hamiltonian density. H equals Hamiltonian density is given by this expression, we know that. So here pi psi dot I is given by H minus L bar. So this is your Hamiltonian density, this is your Lagrangian density. Okay, don't forget. So this must be density. Okay, density factor, because left hand side, right hand side is density, so left hand side must be a density, no other way. So we can, by instead of pi psi I dot, we can replace with H minus L bar. So instead of this we are going to substitute here. So instead of this we are going to substitute here. The first term let it be and the last term also let it be. Now this can be written exactly like this. Okay, del H d cube R minus, so already we know that L, we know that L equals Lagrangian density dV, we know already. So del L is given by this. Okay, del L is given by this. So we can write this as exactly like this. Is it okay? See. Now this del L and this del L will go off, they will get cancelled. Remaining term, first term, this term and last term, we can write exactly like this. Okay, so we have, you just keep this term here, you bring all the terms that side, common terms d cube r, you just have this equation 10.41. So del H is given by this expression. Any doubt? Okay, so the variation of H produced, so H is a function of psi comma pi. Okay, so similarly L, last time we discussed with L is a function of psi comma psi dot. So now the Hamiltonian, H is a function of psi comma pi, we will have to use partial differentiation rule, which is nothing but this. So you have partial dH by d psi del psi plus partial dH by d pi del pi. So again the same thing that we are going to use as we have done 2 slides before. So del H is given by this expression. Okay, you compare this expression with the old expression. This is 10.42, this is 10.41, which you have derived just now. So you compare these two expressions and these expressions will give us, you just compare, left hand sides are equal. So right hand side, your psi dot is nothing but dH by d psi. Is it okay? dH by d pi. And your pi dot is nothing but dH by d psi. Is it okay, or there's a mistake or what? Somewhere there's a mistake. Your psi dot will be dH by d pi. See, psi dot will be dH by d pi, correct. Your pi dot will be minus dH by d psi. Okay, you compare these two expressions. Del pi is there, your del pi. So your psi dot will be this one. Your minus pi dot will be this one. See, pi dot will be minus dH by d psi. This is the equation of motion, and this is the field equation with the help of Hamiltonian's formulation. So they are referred as a classical field equations in Hamiltonian form. Is it okay? Now to find out the Hamiltonian equation for the function, we are going to check whether really that expression resembles with the equation of motion or not. We are going to check. So we are going to introduce function f. We are going to introduce, which is a function of psi pi comma t. Okay, psi, this is a function, this is functional density, any function, and which is a function of psi comma pi comma t. So we can write f exactly which is equal to this. Okay, which is a function of psi pi comma t del v. Now we again use partial differentiation rule. We can get this. So now there are 3 variables, you will have 3 terms. Okay, as we have done earlier. Can you see? There are 2 variables, we have 2 terms. Here we have 3 variables, we can have 3 terms. So as usual, partial df df by d psi del psi plus the second one partial df by d phi del phi plus this one partial df by dt del t. I can bring this term outside because this integrand is with respect to volume. So this becomes constant. I have pulled out. Is it okay? Pulled out. So partial df by dt I have pulled out. The remaining term I have written exactly like this. What is psi dot? Psi dot is dh by df. Okay. Your psi dot equal to dh by d pi. So I am going to replace this by psi dot. This is your psi dot. Psi dot equal to d psi by dt. So this is your psi dot. And the pi dot is nothing but d pi by dt. So in this expression I am going to replace this. Okay. But we know that psi dot equal to dh by d pi. So instead of psi dot you can write dh by d pi. Instead of pi dot you can write minus dh by d psi. I repeat, this is del psi by dt is written as psi dot. Del pi by del t is written as pi dot. But we know that psi dot is given by dh by d pi. So dh by d pi. Similarly, pi dot is given as minus dh by d psi. So this equation can be written as exactly like this. Okay. So you would have studied this expression, which is nothing but your Poisson bracket. So you would have studied in classical mechanics. This is exactly replaced with a Poisson bracket f comma h. You have two variables here. You have two variables f and h. So this is replaced with f comma h. So this is the classical equation of a motion of a function in the Poisson bracket notation. And we know that this Poisson bracket is replaced by commutative bracket divided by IH cross in quantum mechanics. Okay, suppose this function does not explicitly does not depend on time, then this will become 0. And we are going to replace this Poisson bracket into commutative bracket divided by IH bar. So this equation becomes exactly like this. And what is this one? F comma h. Suppose if they commute, for example, if they commute, this will become 0. What are these? F is df by dt, which is equal to 0. This is equation of motion. Okay, so this is what we started with the Hamiltonian formulation, that we are going to find out the equation of motion. So we end up with the equation of motion. It clearly says that df by dt equals 0 if f comma h commutes with each other. They commute with each other. So equation 10.44 defines a Poisson bracket for two functions f comma h of the field variable. So we are going to replace this by Poisson bracket as we have studied in classical mechanics. If h does not explicitly depend on time, this one will become 0. So it is a constant of motion and represents the total energy of the field. Thus the equation of motion for any quantum dynamical variable f is obtained from this equation by replacing the Poisson bracket by the commutative bracket divided by IH cross. Okay. So the above equation describes the behavior of the quantized field specified by the Hamiltonian. Okay, that's the end. So we started with the Hamiltonian from classical mechanics. Okay, then we used the rules, differentiation rules, and also we used the field functions, and we discussed at the end we discussed about the equation of motion. So this is a very important equation. This is about Hamiltonian formulation. So this is the equation, field equation, one of the field equations using Hamiltonian formulation. Okay, we'll see in the next class, students. Bye.